Well, we've got ourselves an action-packed lesson tonight, and we are going to tackle a very curious question tonight. We are going to ask ourselves, what is the area between these two curves? We definitely have curved edges provided by F and G, and we want to know the exact area of this region in here, and we're going to find out how we're going to use calculus and how we're going to use some definite integrals to find that exact measurement. Alright, so let's recall what a definite integral measured in the first place. A definite integral measures the exact area between a curve and the x-axis within the boundaries a and b. Now sometimes the boundaries were vertical lines at x equals a and b, and sometimes a and b were intersection points between the curve and the x-axis. So first of all, if I threw out the integral from a to b of f of x alone, what that integral would do is it would tell me the area of everything underneath f all the way down until I hit the x-axis. Contrary to that, if I did the integral from a to b of g of x, that would tell me the area underneath g down until I hit the x-axis. So basically what I want to do is I want to subtract the red region from the entire black region, and if I do that subtraction, I'm going to be left with what was in between them. So if I do an integral from a to b f of x minus the integral from a to b of g, the answer is going to be the space in between them right here, underneath f but above g. Now we can simplify that expression a little bit. We can combine, because those two integrals do have the same bounds, we could combine them into one integral that just goes from a to b f of x minus g of x. And that, ladies and gentlemen, is how we're going to find the area between two curves. And basically the bottom line is f has to be the upper function and g of x has to be the lower function. And as long as it's upper minus lower, you're going to be in great shape. Just watch out for bear traps as we do go through tonight. As far as the second picture here, the upper function here is g. So as we go to set up this integral, we would go from a to b, and we would just have to put g on top. And then f would be your underlying function, so f minus g with respect to x, and wrap it up. Of course, we're going to see a variety of tricks tonight. Probably the most popular one that the College Board likes to throw at us is they might give us multiple regions here. We want to find the combined area of the two regions. And basically, anytime your upper function changes, you got to stop and set up a new integral. So we've got from a to b, f's the upper function, but from a to c. And then from c to d, things change, and now g becomes the upper and f becomes the lower function. So I would have to use two separate integrals on this one. The first integral would be from a to c, and I would do f, which is the linear function, minus g, which is the cubic function, plus all the area starting at c until I hit d. And this integral would say g of x minus f of x. And in this particular case, there's no way to shorten this one up. Expressing it as the sum of two integrals would be the most concise way to do it. Alright, now, knowing where we're going to be going over the next few days, and after we talk about area today, we're going to progress and things are going to get more complicated, and we're going to do a bunch of volume tricks and so forth. But we need to start thinking in terms of an infinite number of really thin rectangles. Alright, so an infinite number of really thin rectangles, and you're wondering, what the heck are you talking about? Well, I'm going to try to show you here. So on my particular picture here, we've already discussed that if you wanted the area of this green region, it'd just be the integral of f minus g within the bounds a to b, and you're rocking and rolling. But what I really want you to think about is I want you to think about taking this region and slicing it into an infinite number of really thin rectangles. Okay? And there's my first rectangle. Now, what I want to do is I want to just focus on, instead of focusing on the entire region, let's just focus on the area of that one singular rectangle. And that rectangle is going to have an area where we're going to have, its length times its width, basically, or its height times its width. Now, this particular rectangle has a height, let's see, the height right there is going to be whatever f is minus whatever g is. Okay? So actually I just want to do, let's say area equals f minus g, that's his height. Now his width is a little more interesting. Now his width is, we want it to be really thin. And what we're going to do is we're going to say that's the change in x, delta x. It's how much the x values change from, say, like this point on the x-axis to this point here. So now, as delta x gets infinitely small, we're going to call it dx. So we've got f of x minus g of x times dx. And what you'll notice is that's the area of one rectangle. And now we've said we want to split this region into an infinite number of really thin rectangles. And if you want to add all of them together, we're going to use an integral. And the integral is the act of adding an infinite number of rectangles together that are infinitely skinny. So real quick here, before we do jump into our first live examples, I just wanted to really summarize and cut to the chase as far as what we've been trying to express here. The area between two curves, the one thing you've got to know above all else is that as long as f's above g over the interval a to b, then the area between those two curves is given by this integral right here. And just keep emphasizing f is the upper function, g is the lower function, and as long as we get a good sketch and we can identify who's upper and who's lower, life's going to be easy today. Alright, so here's our first live example, and they want us to sketch the region, which is very important, and then we're going to set up an integral to find the area between these two curves right here. One's linear, one's a quadratic, and so I'm going to do the best I can, and of course if you've got one of those fancy sticky graphs, you can pop one of those puppies out and work on a really nice graph here. Let's see, if I want to graph f, I know there's a y-intercept of 3, and it looks like the slope's 1, so just kind of go up 1 over 1 and so forth, and I'm going to have a x-intercept of negative 3 and a y-intercept of positive 3. It's going to look something like this. Okay, now g of x is a quadratic function shifted up 1 unit, and then from that point forward it's going to behave just like x squared would. And let's see, it looks like we're going to cut through there and then pop up on this side and look a little something like that. So what we're trying to do here today is find the area bounded between the two curves. So we're looking for everything in this region right here. And one of the things you're going to quickly realize is that you're going to have to find, or we're going to have to find our own bounds. So we want to figure out that intersection point, and that would be my lower bound. Then we're going to find the upper intersection point, and that would be my upper bound. So in order to find those intersection points, and this is going to be real basic review from an earlier math class, is we're going to set the two functions equal to each other. X plus 3's got to equal x squared plus 1. And so we'll move all the terms to one side. And boy, this is the good old math, isn't it? When life was easy, we didn't realize how easy we had it back in the day. So we'll tee that up. And so I got intersections of x equals 2, which would be this one up here. And the first intersection was negative 1, so this one right back here. And so let's go ahead and set up a beautiful integral to represent the area between those two regions. So the integral from negative 1 to 2, upper minus lower. Upper within that region is going to be the x plus 3 minus the lower function, which is x squared plus 1. And I want you to take a look at my parentheses here. The parentheses around the first function were strictly optional, but the parentheses around the second function is extremely important because what we've got to do next is we've got to distribute our negative sign. And so we've got the integral from negative 1 to 2, x plus 3 minus x squared minus 1. We'll go ahead and we'll combine some like terms here. And we've got negative x squared plus x plus 2. We just kind of like to put them in a proper order. Now we're actually ready to do some calculus. We're going to go ahead and integrate here, folks. Let's get negative 1/3 x cubed plus 1/2 of x squared plus 2x. And my bounds are still negative 1 to 2. Nice thing was there was no u sub was needed. Typically when we're doing our area problems there is no u sub necessary. So I'm going to substitute my 2. I've got negative 8/3. Looks like plus 2 plus 4 minus, let's see, I got a negative times a negative. So that's going to be 1/3 plus a half and then finish with minus 2. So we're going to do some simple arithmetic, combine these numbers and see what we get. So in my first group I tried to express these in thirds, so the 4 would be 12/3 and so forth, and the cumulative total there would be 10/3. And on these guys I'm going to do, it looks like I'm going to have to use a base of 6, so this is really 2/6, this is really 3/6, and this would really be 12/6. And if I combine all those like terms, it looks like I'm going to get negative 7/6, so if I subtract a negative 7/6, that's plus 7/6. and this bear here is really 26. So I've got a grand total of 27/6 to represent the exact area of the region between those two curves. All right, now here's our second live problem, and what you're going to see me do for the rest of the night, for the most part, is just work on the setups only. I do trust that if we do get these set up properly, that you guys are fully capable of doing some great integration and some great plugging in of the bounds to get your numerical answer. So my point of emphasis tonight is going to be getting a good sketch, identifying the right bounds, and getting a good setup. And once we identify who's the upper and who's the lower function. So here would be another great non-calculator question. They would expect us to be fully capable of graphing these two functions without the aid of a calculator. If I graph radical x, and again, if you ever have a brain fart and you forget what radical x looks like, plug in a 0, plug in a 1, plug in a 4, plug in a 9, and kind of get a good looking picture here. Of course, the square root of 4 is 2, and the square root of 1 is 1, and the square root of 0 is 0, so my radical function will look just like that. And the second function, negative 1/4 of x, is a linear function. And he is going to look, let's see, got a y-intercept of 0 and down 1 over 4 units. So a very subtle, slowly decreasing slope. And then we also have a third boundary, the vertical line x equals 4. So what's going to happen is we're trying to find the area of this region right here, rather obscure region. And let's see, who are my bounds going to be? Looks like the left bound is the intersection point, which would be x equals 0, and then the right-handed bound is going to be the vertical line, x equals 4. So let's go ahead and set up an integral of upper minus lower. So let's go ahead, let's see, how shall we say this? The integral from 0 to 4, the upper function minus the lower function. Notice my parentheses are going to help me dig out the correct sign. We're going to end up with the integral of 0 to 4 radical x plus 1/4 of x, and bada bing, bada boom, there's a great setup. Obviously, there would be some integrating left to do and some numerical number crunching, but I think we're fully capable of that. Alright, now our third example is slightly different. This one you would have the aid of a calculator to help you through this one. So we're going to get our calculators out and we're going to practice a few new things, and we're going to just review the storing button and how important it is on a problem like this, because the intersection points are very nasty and we don't want to lose any of the decimal places that are affiliated with those intersection points. Now as far as graphing this rascal, the first one for x squared minus 1, we've got a y-intercept of negative 1, we've got x-intercepts of negative 1 and positive 1, so it's going to look real similar to this bear right here. 3 sine of x. Now, our x-axis isn't necessarily labeled in terms of pi, but I'm going to say, you know what, negative pi is just past negative 3 and positive pi is just beyond positive 3. So from there I can graph the sine curve. I know it's going to dip as low as negative 3. It's going to come way down here. It's going to go through the origin. It's going to go way up to positive 3 and hit pi right in there. So the region that we are attempting to tackle is this region right in here, and I'm going to use my calculator to find this intersection point and the second intersection point up here, and we're going to talk about how to store those rascals. Now, as far as getting a good window, I made sure that I have a couple of keys here. I want to make sure that your calculator's in radian mode. We're going to always leave our calculators in radian mode while we're in calculus. What we're going to do is I did a zoom trig, which if you go to your zoom menu is going to be number 7. Alright, zoom trig was choice number 7 for me. And then what I'm going to do is I'm going to go do an intersection, and I'm going to find the first one there that's just in the third quadrant. So of course, so you go to the calc menu, which is above your trace button, and the calculator is going to ask you 3 questions. Going to ask you who's the first curve, who's the second curve, and where do then they want you to guess. And then the calculator will print the word intersection on the lower left-hand corner of your screen, and I got x equals negative 0.3067554. But of course, that number goes on forever and ever. Now, magically, right now, without us even doing anything, the calculator has already stored that digit in alpha x. So what I'm going to do right now, before I find the second intersection point, I'm going to hit second quit. That's going to take me back to my home screen. And I'm going to type in x, and then I'm going to type in store. So right now my screen has x and an arrow on it. If you haven't used the store button before, it's in the left-hand column towards the bottom, just above the on button. Alright, now what you're going to do is you're going to hit alpha A, and then enter. So we typed in alpha A. Alpha was this, again, left-hand column second from the top, and A was the left-hand column third from the top. And now, what the calculator's done is it's saved that entire number with an infinite number of decimal places so that our accuracy is going to be spot on. And that's mandatory for the AP exam. If we accidentally rounded this number off right here, that's going to affect our final answer down the road, and we're going to be off. So now I need to hit the graphing screen. I'm going to go back to graph, and I'm going to go find that second intersection. For my second intersection, I got x equals 1.946877. Now, of course, there's an infinite number of decimal places, so I'm going to hit second quit again. It's going to take me back to the home screen. I'm going to type in alpha x. I'm going to store it, and then I'm going to use alpha b. Now, the important thing that I want to point out is we had to go back and store the first one before I found the second intersection point, because as soon as you find the second one, it deletes this one from alpha x's memory and replaces it with the new one. So you have to store that first one in A before we go find the second one. Now from here, the integral is going to be real short and sweet. We're going to do the integral from alpha A to alpha B, and as long as I've kind of put this evidence on my paper, I'm just going to use, whoops, that's supposed to be a B. I'm literally going to use alpha A and alpha B on my setup. Who is the upper function? I believe within the region that we're focused on, 3 sine of x was the upper, minus the lower function, which was x squared minus 1. Ladies and gentlemen, from there, I just want you to type this integral into your calculator, and then let's compare answers. So again, I went to the math menu, chose choice 9, and I literally typed it in exactly the way you see it. I typed in alpha A, alpha B. I didn't type in the numbers themselves. When my calculator spit out my answer, I had 3.746030534, yada yada. Now here's the one moment when you cross the finish line, it's only your final answer that can be reported to 3 decimal places. Everything else has to be reported in its entirety. But that's my final answer. Okay, again, here's a real feisty calculator one, so let's try to type in these two functions and let you come up with the appropriate graphing window. Obviously, the more effort you put into it right now in this moment, the better off it's going to pay down the road. And just you may not come up with a real good window the first time, but just keep chugging along and keep altering it and tweaking it until you get a nice one. Alright, so what I did is I used alpha F1. I love alpha F1. So assuming you have the updated calculator, if you go alpha F1, that's right above the y equals button, you're going to be able to type this sucker in as a fraction. You're not going to have to worry about the parentheses or anything like that. And my function kind of looked like, let's see, I'm not worrying about exact points right now. I'm just getting a good sketch down. It does go through the origin, it looks like, and then it kind of tails off in that direction. The natural log function, though, we could have done that one out of the calculator. It's got a vertical asymptote at -5, and then it's going to cross at -4, and it looks like it's going to kind of tail off in that direction there. And then, of course, we also have the vertical line x equals 3. So we're talking about this region right in here. And I'm going to get the 2 intersection points, just like on the last one. I'm going to store, well, actually, I only need the first intersection point, don't I? So we're going to go from alpha A up to x equals 3. The upper function is going to be the natural log minus that big old fraction, 3x squared all over x squared plus 2x plus 5. And at the end of that entire string, let's throw a dx on the end of that entire thing. So, once we found the intersection point and stored it, we got to set it up. So we've got upper minus lower, upper here minus lower there, and you're good to go. Alright, we've got just a couple more to go, and of course we've saved the big bears for the last here. And I want to find the area of the region bounded by y equals, let's try negative x squared plus 3x. And let's try the curve y equals 2x cubed minus x squared minus 5x. Now, a couple of points of emphasis here that I really want to drive home today. Number one, take the time and put the energy into getting a great sketch. Okay, this is going to be a non-calculator problem, believe it or not. I know it's a little overwhelming, but I'm going to show you how to fight your way through it. And then just really focus on once you get that great sketch, focus on the correct bounds, and let's really pay attention to who's upper and who's the lower. All right, now, as far as sketching these rascals, we got to find the roots first, and we got to know which way these parabolas and these polynomials open up. So if I focus on the first one right here, I pull out my GCF, and it looks like I'm going to get roots of 0 and positive 3. And it looks like that parabola is going to open down. So I'm picturing, real rough, I'm picturing something like this, goes right through the origin. Now as far as that second function, again, I'm going to pull out a GCF of x, and that's going to leave me with 2x squared minus x minus 5. And it looks like it can factor a little bit more. And I'm going to break it, a little guess and check style of factoring. And why don't we say we go with minus... Oh, shucks. I think I just goofed myself up. Yeah, I don't think this one does factor anymore. Well, at least we know one of the roots is going to be at the origin nonetheless. But I guess we are going to have to use our calculator here to find the rest of the roots and get a good sketch on here. The key here is with the great sketch, and this is what I want you to be able to take home with you tonight, is that when you do get that good sketch going, and I've kind of imported a really nice looking picture of this one, just like we said, the quadratic had roots of 0 and 3, and it opened downward, and then we had this cubic equation that had the two turning points in it, and what we did is we found an intersection at -2, and then the one at the origin, and then there was another one at +2. How did we find those intersections? All we did is we set these functions equal to each other, and once we set them equal to each other, you moved all the terms to one side, and that one did factor nice. So let's go ahead and ask ourselves, can I find the area of these two regions using just one integral, or do I need two integrals? And the one thing that I really want to preach here is that we absolutely need two integrals. There's no way that I can condense this into just one integral. Alright, so the first integral is going to go from x equals -2 up until x equals 1. And within that interval, I'm going to say the pink graph is the upper and the blue is the lower. So I'm going to start off with 2x cubed minus x squared minus 5x minus the quadratic -x squared plus 3x. Okay. Plus, the second integral is going to go from x equals 0 up until x equals 2. And this time, the quadratic is the upper function, and the cubic is the lower function. So just using lots of parentheses here, I'm trying to stay organized, very deliberate and detailed here, and finish with a dx. And the sum of those two integrals would be our final answer. Okay, we're going to finish with a nasty one here tonight. We're going to ask ourselves, well, what happens if the functions are in terms of y? So all the functions we've worked with predominantly in our entire math career were always like y equals 2x plus 3, and we said those were in terms of x. We're going to switch gears now. We're going to talk about what if our functions are in terms of y. And you can kind of get a taste of it here with the notation that we're using. We're saying x equals g of y instead of y equals g of x. X equals f of y, or over here you could say x equals y plus 1, or x equals 1/2 y squared minus 3. Believe it or not, as nasty as this sounds, once we practice these a few times, it's going to be easier to do some problems in terms of y. And we need to start thinking of our representative rectangles that they now must be horizontal. Okay, so that's going to be mandatory. As soon as we're talking about things in terms of y, we need to get our rectangles going horizontally. We're going to think. No longer are we thinking upper minus lower, we're thinking right minus left. The length of this rascal right here is f of y minus g of y, so we need to start thinking right minus left. As I set up my integral, it's now going to be the integral from c to d, so you can see how we're starting at c and we're ending at d. And then we're going to do right minus left, f of y minus g of y. And what are we going to put at the end? Yeah, we got to put a dy at the end. Now to just practice this one a little bit, visualize your rectangle really thin. And we're going to do an integral from, we're going to start with -2 because we're starting with the y coordinate. And we're going to end up here at +4, again, the y coordinate of the intersection point. And we're going to do right function minus the left-handed function, which would be 1/2 of y squared minus 3, and again with respect to y. Alright, so here's our very last example of the night. You guys have been troopers for hanging in there. I know this is a big topic, and we certainly don't want to cut any corners now that you've made it this far. So I want you to find the area between x equals 3 minus y squared. So again, right off the bat, you notice this function's in terms of y, and then also x equals y plus 1. Now, when it comes to graphing these functions, it could be a little uncomfortable. So the first function, what you'll notice is if you set that first function equal to 0, you're not finding the x-intercepts anymore, you're finding the y-intercepts. And so you get plus or minus radical 3. And let's see, so that's going to be radical 3. This is going to be negative radical 3. And then if you substituted a 0 in for y, you get an x-intercept of positive 3. So we got 1, 2, and 3. So my parabola is going to open to the left. And the reason it's opening to the left is because the y squared was negated up here. So there's my first function. Now my second function is just linear. Again, if you want to find the x-coordinate, or I'm sorry, the x-intercept, you would substitute a 0 for y and get a 1. If you wanted to know his y-intercept, you'd substitute a 0 for x and get negative 1, which would be down here a little bit. And so we get a nice linear function that looks like this. And what we've got to do is we've got to find these two beautiful intersection points right here. Specifically, we're going to focus on the y-coordinate. So I'm going to set the two functions equal to each other, just like any other time you want to find intersections. Move all the terms over. Y squared plus y minus 2 factors very nicely. So we got y plus 2 times the quantity y minus 1. Roots are going to be y equals 2, which is this guy right here. And y equals positive 1. Oh, goodness gracious, that should have been a negative 2, shouldn't it? I was going to say, that doesn't feel right. So the negative 2 would be down here, and the positive 1's the one on top. All right, so let's go ahead and we'll set up an integral now. And again, we're not thinking upper minus lower anymore. We're going to think right function minus left function. And so as we do so, my first bound is negative 2 because that's where the first intersection was, and again that's y equals negative 2, and then y equals positive 1 is my upper bound. Right function is going to be the blue curve, which is 3 minus y squared, minus the left-handed curve, which is going to be y plus 1. Throw a little dy on the end, and ladies and gentlemen, we've got ourselves an integral to represent the area of this region right here. So good luck tomorrow. Hope it went well. Keep working hard, and we'll see you tomorrow.